Hello everyone. Today I'm going to talk about our work called C2MIL, which stands for Synchronizing Semantic and Topological Causalities in Multiple Instance Learning. This is a collaboration between USTC, Xiamen University, the University of Hong Kong, and our partner in France. Graph-based multiple instance learning is widely used in survival analysis with hematoxylin and eosin-stained whole slide images. But when we use them for survival analysis, we face two big problems. The first is semantic bias. Slides from different hospitals can look different. For example, staining, sectioning, or scanning may change the color and texture. The model may pick up these shortcuts instead of real biology. The second is topological noise. When we build graphs from patches, not every region is important. In some cases, tumor is relevant, but background or stroma may confuse the model. So, to make survival prediction both reliable and interpretable, we need to remove the semantic bias caused by slide preparation, and at the same time identify the truly causal subgraphs that carry prognostic information. People have tried several approaches. Stain normalization and contrastive learning help reduce bias, but they don't cover all preparation variations. Causal MIL methods attempt to remove confounders, but usually require complex pipelines and manual assumptions. Graph-based MIL captures structure, but doesn't distinguish causal subgraphs from irrelevant ones. So, there's still a gap. We need a model that can handle both semantic bias and topological noise at the same time. We propose C2MIL, which is built on four main ideas. First, it introduces a dual causal framework that removes semantic confounders and identifies causal subgraphs relevant to survival. Second, we design CAFT, an adaptive module that disentangles semantic bias without the need for prior knowledge. Third, we develop a Bernoulli differentiable subgraph sampler, allowing stable and efficient learning of causal subgraphs. Finally, we bring all components together with a joint optimization strategy, ensuring they interact coherently under a unified causal principle. Here's the theoretical analysis of our proposed dual structural causal model. Trivial features like color or slide count, we call them T, affect both the input and the label. The input WSI forms a graph G. Inside that graph, there are useful subgraphs C and irrelevant ones S. Only C should affect the outcome. So, our model does two things: backdoor adjustment to remove the bias from T, causal discovery to find the right subgraph C. This is the overview of C2MIL. For the semantic part, we proposed cross-scale adaptive feature disentangling module. It looks at both thumbnails and patches to learn preparation-related biases. We use learnable cluster logits to dynamically decide how many clusters of bias exist. Then we subtract these biases from the patch features. The result is cleaner, bias-free features that focus on biology rather than slide preparation. On the topological side, we propose a Bernoulli subgraph sampling method. The graph transformer estimates the probability that each patch belongs to the causal subgraph. We sample subgraphs randomly and use a straight-through estimator so training remains differentiable. This way, the model doesn't just mask features, it actually learns meaningful substructures while avoiding overfitting. To bring everything together, we use a joint loss with 4 parts, standard Cox loss for survival prediction, an MSE term to make sure disentangled features are consistent, a contrastive term so causal subgraphs align with the full graph, but stay away from irrelevant parts, a ratio loss to keep causal subgraphs compact. This balance makes the model accurate, robust, and interpretable. We tested C2MIL on 3 TCGA datasets. In 5-fold cross-validation, our method consistently outperformed all baselines. In out-of-distribution validation, which is much harder, C2MIL still achieved strong improvements. And Kaplan-Meier curves show that our predictions clearly separate high-risk and low-risk patients. The ablation studies show that every part of our model matters, and that our modules can be added to different baselines to improve existing MIL methods. From the parameter analysis, weighting each part of the loss by 0.1 gives the best results. Also, adaptively learning the number of clusters outperforms using a fixed number, and gets close to the ideal case. Visualizations also tell a nice story. CAFT automatically clusters slides by preparation style, and our attention maps line up much better with tumor regions compared to other methods. That shows the model isn't distracted by noise. WSIs. It removes semantic bias, discovers causal subgraphs, and delivers better accuracy, generalization, and interpretability. In the future, we hope to extend this idea to other MIL tasks, like classification or detection, even in cases where building a graph is not straightforward. Thank you very much for watching the video.